Now, we're skipping lots of sections of Chapter 2, and we're continuing our little review of Math, what used to be Math 100. Uh, so if you need some background on this, again, you're going to have to go back and look at some of these things. So we're skipping section 3.1. We're jumping right into 3.2, where we're going to deal with systems of linear equations, which has a lot to do with graphing. So here, what we're doing, to give you a little background, uh, these are all linear equations in two variables that can be put on a graph. So if we put one line on a graph and we get this equation here, and this equation is the graph, and we plot another line, but when we plot this other line, the graph looks like so, an interesting thing happens, and this will be for background. Now, along every graph, there are ordered pairs that we were showing a little bit in the previous lesson. How many ordered pairs are along this particular line? Well, we say there is an infinite number. And how many ordered pairs are along this line? Well, every line of a graph has an infinite number of ordered pairs. Now, when you plot two or three of these ordered pairs, you can create a line, and that gives you, again, others that would be everywhere along the line. And since the line extends in an infinite direction, in each direction, there is an infinite number of ordered pairs along this. But notice what happened here. When we made a graph of this blue line and then a red line, and they were different equations, an interesting thing happened right there. The lines intersected. So the ordered pair of this particular intersection, just sketching this in, what is that ordered pair? Well, it's over 1. That's going to be a -1 for the x value, and then up to a +2 for the y value. So this unique ordered pair, this set of coordinates, is a solution for this red equation and a solution for the blue equation. So we say we had systems of equations that we solved simultaneously. In this case, by making the graph of them. Now, we're not reviewing how to do that at this time, but giving you a little bit of background. Now, as we think of lines along a graph, suppose I make a first line that is red, and I draw another line of another equation, and it ends up looking like so. And what do you notice about these? Well, are they ever going to intersect? And the answer is no, because they are parallel lines. So will there ever be this unique intersection of parallel lines? And the answer is no. So for a system of equations in which there are parallel lines, there is no solution. Now, a third scenario might be that you draw your first line like so, and then you are working the equation and you draw your second line, And lo and behold, the second line goes right on top of the first line. I'm off a little bit here, but they go right on top. So again, we said there were an infinite number of solutions in each of these lines. And since the lines are the same, what is the number of solutions for something like this? Well, we say there's an infinite number of solutions. So these are the three scenarios that you get when we are solving systems of linear equations. And if we were graphing them, this would be the results. If we got one ordered pair, that would be the unique solution where these two lines intersected. If there were no solutions, the lines would be parallel. And if it's the same solutions, there's the same lines, it's an infinite number of solutions. So this is what we're going to get, and we're going to use algebra instead of graphing to figure out what we have here. So let's take a look at our first one. Our first one, we're going to take a look at this, and we're asked to solve it the algebraic way through substitution. So let me write this up here. X plus y equals a negative 8. And we also have a second equation. We can number these if we'd like. The second equation is y equals 2x plus 1. And we're going to use the method called substitution. Now what that involves is that we're saying the value for y in terms of x is 2x plus 1. This is what y equals. Y equals 2x plus 1. So what we're going to do is write our value of y, which is 2x plus 1, in the other equation, and let this value replace the letter y. We're going to have this substitute for y, because that's what y is. Now we rewrite it. We're going to go x, this is the first one, plus y, which is this, 2x plus 1, equals a negative 8. That's the key to what we're doing, and you should have in your notes. So now we combine like terms. We get 3x plus 1 equals a negative 8. We get 3x. We're going to transpose that. That becomes a negative 1 on this side, so a negative 9. We're then going to solve for x. And here we have to be careful. We get x equals a negative 3. So we now have one member of our ordered pair of where these lines, if we drew them, would intersect. Well, if x is a negative 3, we could put that negative 3 right there. 2 times negative 3 is negative 6 plus 1. Our y then is going to be a negative 5. And we have found that point of intersection by using the method called substitution. Later we'll do this method. And there's the example of it. So this is something you will need to know and be practicing to gain mastery in solving systems of linear equations in two variables when you can solve for one letter, and then use that to substitute in the other equation. Okay, let's look at B. Now B is sort of an interesting situation where we have y equals something and y equals something. So in a sense, we can set it up as y equals y. And what is that first y? Is 3x plus 5. And our second y is a negative 2x plus 1. So y equals y, and now we solve for y. Transpose that, 5x. Transpose that, and we get a negative 4. So we're going to get a fraction here. We get x equals a negative 4/5. So I saw some fractions coming up here. Checking my work, transpose that, makes it a 5x. Transpose that, makes it a negative 4. Divide both sides. X is equal to a negative 4/5. So I'm going to use this first equation here to put my negative 4/5 in there for x. 3 times a negative 4 is a negative 12/5. I have to convert my 5 into a denominator of fifths. So that's 25/5. This is 5. But now I subtract 12 from 25 and I get 13/5. So our ordered pair is this and this. If we look at the answer, there it is. Okay, so this one is going to be all real numbers, and this is the way they show it. This one's going to be no solution. This one's going to be this ordered pair. And this one is going to be some big numbers. Again, we're not going to do all of these because it makes the tape too long, but let's do at least a sample of some of them. So we will be going over strategy of what to do. So as we look at letter C, there is y by itself. So I've rewritten it. Y is this. So I'm going to take that and put it where y is in the other equation. So I get 4x minus 2, and here's where I'm going to put my value of y in there. 2x minus 12 equals 24. So I've gone from a system of equations with two variables, x and y, to now an equation through substitution with only the letter x. So I can do that. So I clear parentheses, 4x minus 4x. Negative times a negative gives me a positive. 24 equals 24. Okay, now interesting thing happens here. Look at what happens to my x's. They just cancel out. So I'm left with the statement 24 equals 24. Is that true? Yes, it is true. Now, what happens when we do substitution and our letters cancel out and we end up with a true statement? This is a case where if we would have graphed them, they're actually the same line. So how many solutions did we say we have along that line? Well, there's an infinite number of solutions because, in fact, these two equations are just different forms of the same equation. So how do we write the answer? Well, we write the answer using set builder notation. Looks like this. We say x comma y is such that, and we write either of these equations, 2x minus 12 equals y. Now we could have written the other one. You only have to write one. And in MATLAB, they're going to give you choice A is one ordered pair. Choice B is no solution. And choice C will be one of these. Okay? So if you get a unique pair, you put the ordered pair there. Now, if you get something like this and it says 3 equals 10. The x's or the y's would cancel out and you get a not true statement. This is false. Then your answer is no solution because these lines are parallel. That is, they would have gone like sort of like that, okay? In substitution or the other method, elimination, this is what you get. Okay, I'm not going to do another one because we're already at 15 minutes. I wanted to show you the method of substitution here. Okay? Now I do have other videos in which I work out a lot more. This is meant to be a review of the strategy, not necessarily doing every problem, and the answers are down below. Okay, we're now going to do elimination, and I'm going to raise it up just a little bit here, but I need to have the room up here so that I could write these out. When we do elimination, now we could do substitution for this one, but they're asking us to do elimination. In elimination, what we do is we write the first equation as the number 1. We go 3x minus y equals a negative 5. Then we write the second equation right underneath it, which is x plus y equals 13. Now, both of these equations are in what we call standard form. Standard form, you recall, maybe ax plus by equals c. So you have your x term, your y term, and a constant. That's what we have here. Now, when we set them up in standard form, notice if we just put a line underneath them and we add them up together, then this becomes 4x. This cancels out. This becomes a 0. And this is going to become an 8 here. So what we did by putting them in standard form, which they were already, by the way, and just adding them up, this cancels out. We have eliminated the y's. That's this method, the elimination method. We're looking through addition to eliminate one of our variables. And we're going to get here x equals 2. So again, we have one of our ordered pairs. Now, we then take our x, put that in either of the equations. X is 2, let's say. So what are we going to do? We're going to take that 2 to the other side here, and that becomes a negative 2. So 13 minus 2, that's 11. That is my first ordered pair using the elimination method. Now, you will get times when there are the infinite number and which there are no solution. And basically, it's very similar to what we just did. If the letters eliminate and you get a true statement, it's an infinite number of solutions. If you eliminate the letter and you get a untrue statement, like 5 equals 2, then that would be no solution. And this is what they're asking you to state. So let's do another, and we'll set this up what we did up there. This is going to be equation 1, and this is equation 2. So we'll put them in standard form. 5x minus 2y equals 7, and 8x plus 2y equals 6. Now, they're giving us easy ones because look at, we didn't have to do anything. Just put them in standard form, and here the y's are canceling out. So this is 13x. This adds up to 13. X equals 1. So it couldn't have anything easier than that. If x is 1, we can use this one here. This is going to be, I'll change colors so you can see it better. X is going to be a 1 here. So this is 8. I'm going to transpose it to this side, becomes a negative 8. So I now have 2y equals negative 2. Solve for y is a negative 1. Wow. Again, both easy, and we want to start easy. This was using the elimination method where we set them up in standard form, add them up to eliminate one of the variables. And then once we find one, we solve for the other letter. All right, let's try letter C now. And that shows us what we have to do often when we do these. This is equation 1. This is equation 2. Now, fortunately, they're in standard form. So 4x minus 5y equals a negative 1. And then here we have 8x, a negative 8x, plus 10y equals 4. Now notice you can't put a line and add them out. One's not going to cancel. So here's the creative part. We're going to take this first equation and make it an equivalent equation by multiplying it by something, every term by something, so that one of the letters will cancel out. And this is where we kind of use our smarts to figure out what we're going to do. Now this is already a negative 8x. What do I have to do to make this a negative 8x? I have to multiply it by well, we don't want it negative. We want it a positive 8. Okay, it's already a 4. Just multiply it by 2. Okay. So now we're going to multiply this equation, every term, and we put that over here. This is a good strategy, a good technique for doing it. You write this standard form, then you're changing it, and you're going to put the new equation over here. So this is 8x minus 10y equals a negative 2. Now, it's not the same equation anymore, but it's equivalent. And now we just write the other equation underneath it. Negative 8x plus 10y equals 4. Look at this. When I add these up, these cancel out. When I add these up, these cancel out. So I get on this side a 0, and this is going to be 2. Now, does 0 equal 2? No, this is false. When you get a false answer, there is no solution. False answer, no solution. If this ended up 2 equals 2, that would be true. That would be an infinite number of solutions, but that's not here. And if you ended up with y equals something, then you would get a coordinate pair. We don't have that here. Okay. Let's go on. And let's do D. D looks a little challenging, and it's probably going to be big numbers. Now, these others, again, are done in a similar fashion, but they get to be tedious. So here we have 20x minus 15y equals a negative 50. And here we have a negative 6x plus 9y equals 33. All right, so we have to look. Now we want to always try to keep it easy. In fact, all right, we'll just deal with what we have here. I'm going to have to modify and this is the creative part of this. I'm going to have to modify both of these. So that one of these terms cancel out. Now, since this one is negative already, and this one's positive, if I multiply this by a 3, I make this a 60x, and I multiply this by a 10, I make this a 60x. So that's what I'm going to choose to do. And I'm going to pause to do it. Now I'll take it item by item. 3 times 20x is 60x. 3 times a negative 15 is a negative 45y. And 3 times a negative 50 is a negative 150. And this is 10 times a negative 6x, a negative 60x. So this is what I was shooting for. And then 10 times 9 is 90y. And 10 times this is 330. So now I put my line, and I have to add up my columns. So I get 45y equals 180. Divide both sides by 45, I get y equals 4. And you have to, again, there's a lot of algebra, and it takes time to check your work. Now, if y is 4, let's see what we have here. Which one should I use? Let's use this one. Negative 6x plus 4 times 9 is 36 equals 33. Transpose that, that becomes a negative 3 because it goes over as a negative 36, giving me a negative 3. Now I'm going to divide both sides by 6, a negative 6. I get x equals 1/2. Okay. These are my ordered pair, 1/2 and 4. And how did I get it? Well, I put my equations in standard form, and hopefully you're not going to get any that are this tedious. We had some real easy ones, but then we got some that are more challenging. We had to modify each equation. Do it carefully, watch the signs, just think of all the algebra going on here. Then we solve for 1. Then we put that in the other equation, and we got our other value. This is the process of elimination, and this was 30 minutes long. Okay, we're going to wrap this one up.